no rotation, right? So what causes this rotation of the pulley? So that is the friction between this pulley acceleration of that block is in the horizontal direction, whereas the other block can move only in the upward or downward direction because of the normal force. He is applying a force on the ladder, the ladder applies a force on him in the upward direction. In the last class we were talking about the tension in a string. Now we will get this pulley into our discussion. What is a pulley? A simple setup, just like a wheel over which we have placed a string. At the end of the strings, two blocks are attached, right? Now, this pulley does the job of only changing the direction of the string. Apart from that, it doesn't do anything. See, if this pulley was not there, so this string will be straight. So both the blocks will be moving in the downward direction with the same acceleration. But if the string is placed on the pulley, the direction of the string is changed, the direction of the acceleration of these two blocks, okay, they are different, okay? But both the blocks move with the same acceleration. If this block moves upwards with some acceleration, the other block moves downwards with the same acceleration. The acceleration of this block and that block are same, but their directions are different, okay, because of this pulley. So the pulley just changes the direction of the acceleration of the other block, or it changes the direction of the string. That's all, okay?
The pulley doesn't seem to rotate.
See, in this chapter, pulleys don't rotate because we are going to consider only pulleys which are ideal. What is an ideal pulley? A pulley which is massless, frictionless, a smooth pulley, right? That means there is no friction between the pulley and the string. So that means without any friction, so there is no rotation, right? So what causes this rotation of the pulley? So that is the friction between this pulley and that string. So there is no friction because this is a frictionless smooth pulley. So this ideal pulley is what we are going to use for all our questions, right? So the other type of pulleys, right, which can rotate, so that we are going to deal with in later chapters, like the rotational dynamics and the other chapters, right? Here, pulleys are ideal. That means frictionless, massless. That means the tension does not change. If the pulley rotates, there is a change in the tension on this part of the string and that part of the string, because of the friction there is a resistance force, right? So that creates a change in the tension, okay? But because it is a smooth pulley, it behaves more like a hook, right? So there is a hook and there is a string over this. So does the hook rotate? Nothing. So it only changes, it only supports that string, right? So other than that, it does nothing. It just supports the string. Now here, this pulley does not rotate. So that means it is very smooth pulley. So there is no friction or no resistance. That means the tension in this part of the string and tension on that part of the string, so they are same, right? So that means there is no change in the tension. At any point on the string, the tension has the same value, right? So at least the magnitude of the tension is same at all the points on the string, right? If this pulley was not ideal, so that is not the case, right? Tension may be different on this part and that part, but here we are going to consider only ideal pulleys, which is massless and smooth. So there the tension remains same at every point on the string, okay? So we are going to use only this ideal pulleys for our questions. Let us do some simple questions based on this pulley, okay? In the advert machine given in the figure, find the acceleration of the blocks, the tension in the string, and the force exerted by the pulley on the ceiling. See, this simple pulley block system is also called by the name advert machine, though we don't use the term much. These two blocks are attached to the two ends of the string and the string is placed over this pulley. See, even without it being mentioned in the question, you have to assume that the pulley is ideal. That means it is a massless and smooth pulley. In this chapter, all the pulleys are ideal. So we can assume that at any point on the string, the tension has the same value, right? The magnitude of the tension is same at all the points on the string because this is an ideal pulley that does not change the tension. So that is one thing, the tension is same, right? The tension acting on this block and tension acting on that block, they have the same value, okay? One thing. Now we have to find the acceleration. Now when this block moves up by a distance of x units, that block goes down by the same distance. That means the acceleration of this block and acceleration of that block has the same value. Maybe the directions are different, one is moving upwards, the other one is downwards, but the accelerations of these two blocks have the same magnitude, okay? So that acceleration is what we need to find. We have to find the tension and also we have to find the force acting on the roof, okay? Yes. Now let us find one by one, okay? Now let us write the equation for this block of mass small m, right? What are the forces acting on this block? So gravitation force is acting in the downward direction, tension is acting in the upward direction. So tension is the leading force, right? So the block is moving upward. So tension and the gravitation force in the downward direction, these are the only forces. So this is for the block of mass small m. Okay, so tension is the acting in the upward direction and minus the gravitational force in the downward direction, that equals so mass times the acceleration. So that is for this block, and similarly for the other block that is going downwards, so that means gravitational force in the downward direction and also tension in the opposite direction. So for that block, so the gravitational force mg, so that is in the downward direction, and tension in the upward direction, we have taken the downward direction to be positive for this. Okay, so that equals the mass times the acceleration, same acceleration, we are using the same letter here, same acceleration, because both the blocks have the same acceleration, at least the magnitude. Okay, now we have to simply solve this to get our required answer, that's it. Okay, so what do we have to do? So can we simply add these two? So if you add these two equations, so t gets cancelled, so we get m minus m multiplied by g equals, okay, m plus m multiplied by a. So that's also, that gives you our required acceleration. So acceleration equals m minus m divided by m plus m times g. So that's all, that is the acceleration of both the blocks, right? So both the blocks move with the same acceleration, the magnitudes of the acceleration. So m minus m divided by m plus m g. So that is the acceleration. Now you want to find the tension, so then you can substitute in one of the equations. So any one equation, you can substitute this acceleration either here or here to get our required tension. Suppose you substitute in the first one. So required tension equal to, so this is mg plus ma, m multiplied by this value. Okay, so that is m minus m divided by m plus m multiplied by g. So let's simplify this. So here, so mg plus m square g, and here also we have minus m square g, that gets cancelled, so mg, here also mg. So if you simplify, you get 2m capital M divided by m plus m multiplied by g. So that's it. So that is the tension, okay, in the string. Okay, so that is the answer to one of the questions. Okay, tension is found, the acceleration is found. We also have to find the force on the ceiling, right? The force exerted by the string, okay, on the ceiling. So what is that force? So let us find that force. This is the tension on that string, right? That string. Now we have to find the same tension on the string which connects the ceiling to that pulley, right? That tension we have to find. So let us take that tension to be, say, T1. Okay, T1 is the tension. See, that means it is like this. So this is the string. So T1 is the tension. There is a pulley, and this tension is T, which we have found. Now this pulley is massless, right? So that means, so what are the forces acting on this pulley? There is a tension in the downward direction. So this is driving this like this, downward direction, and this tension is in the upward direction. Okay, it's upward direction. Now, so these two forces balance each other, right? Or if you use simply Newton's second law, so what are the forces acting on the pulley? So what are the forces acting on the pulley? So T1 in the upward direction, T1 minus, so T here, T here. So 2t, right? You have to add these total, right? So 2t is the force acting in the downward direction. So 2t, that must be equal to mass times the acceleration. But what is mass of that pulley? So that is 0, right? That is an ideal pulley, so massless, so 0. So T1 equal to 2t. So T1 equals 2t. So that's all. So t is already found here, so that can be substituted here also. So 2 times that, which means 4m divided by m plus m multiplied by g. So that's also, this is the force acting on the ceiling, right? Yes, so that is one of the answers, right? The tension in the string is this one. So this is the tension in the Atwood machine, right? Simply you can remember this as a formula if you want, right? Sometimes if required, we can directly use this result in questions. And similarly, the acceleration of the two blocks in the Atwood machine, so that is this formula. Okay,
Is it a formula to be memorized?
no, it is not necessary to remember this, but some teachers would suggest that you memorize these values. But there is a limit as to how many things you can memorize, right? You can do these 2 steps to get the answer. But if you remember this, that will make your calculations easier in some cases, right? So that's up to you. So you've got the answer, tension and the acceleration of the blocks, right? So that is the answer. The acceleration of the blocks given in the figure is. Here also we have 2 blocks connected by a string, but the string is going over a pulley which is attached to a wedge. So one of the blocks is moving in the upward or downward direction, right, vertical direction, but the other block can only move along the inclined plane, right? So almost the same idea that we used in the last question, but The motion of the 3 kilogram block is along the inclined plane, but the gravitational force is acting in the vertically downward direction. So we have to take its a component, right, in the direction of its motion. So that is the only difference. Otherwise, it is similar to the last question. Yes. Now let us consider this 2 kilogram block. What are the forces acting on this block, right? So 2 kg block. So let us assume that this 2 kg block is moving upwards, right? So we don't know whether it is moving upwards or downwards, because so that is 3 kilogram block, which is heavier. So we assume that, so that block is moving downwards, but this is moving upward. So we don't know. Let's see. Now 2 kilogram block is moving upward. That means the tension force, the tension in the string. So that is the force which is taking this block in the upward direction. So against which we have the gravitational force in the downward direction. So what are the forces? Tension in the upward direction minus the gravitational force in the downward direction. So 2 kg, which means 2g. That equals the mass of this object is 2 multiplied by acceleration. So this is for the 2 kilogram block. Similarly, we will write for the 3 kg block. Okay, so 3 kg block. So that is moving down along the plane, right? Yes. Now what are the forces? Now tension is acting in the opposite direction, but the component of the gravitational force in the downward direction. So we have to take the component of gravitational force along the plane. So what is this? Mg multiplied by that angle. See, the angle made by that incline with the horizontal is 30. That means that angle is 60 degree. That means this is take the component, right? So cos 60 degree or sin 30. Okay, so that means the force is mg. Mg means 3g cos 60 degree. Okay, this is the component of the gravitational force, and the tension is acting in the opposite direction. So minus t. So that equals mass times the acceleration, 3 times acceleration. See, same acceleration, right? Both the blocks move with the same acceleration, because when this block move upward by distance x, that 3 kilogram block also moves down by the same distance x, right? They move together because they are connected by a stretched string. Okay, so that means both of these blocks have the same acceleration, magnitude. Okay, so same a. Okay, so that's all. These are the two equations. Let us solve them to get the accelerations of these blocks. Okay, yes. Let's simplify. This tension is not what is asked in the question, so we can just add these two. Simply add these two equations. We get, what is that? 3g cos 60. Okay, let me write as it is. So 3g cos 60 minus 2g equals 5a. So this is 3g multiplied by 1 by 2 minus 2g equals 5a. So this gives you, so 3 by 2 minus 2. So it is minus 1 by 2g equals 5a. So that gives you our required acceleration. So that equals minus g divided by 10. So this is the acceleration of the object. We can take the approximate value of g to be 10. So that equals minus 10 divided by 10. So minus 1. So minus 1 is the acceleration of both the blocks. Is that okay?
The negative sign is because we assumed the wrong direction.
Yes, we had assumed that the 2 kilogram block was moving upwards, right? But actually it is moving downwards. That is why we are getting negative acceleration. If we had assumed that the 2 kilogram block was moving in the downward direction, we would have got the acceleration positive itself. So initially we didn't know, so we took some direction as positive direction. So the blocks, 2 kilogram block was moving upwards. So that was the direction we took. But we got a negative sign. So actually the block 2 kilogram block is moving downwards. So that 3 kilogram block is moving upwards, even though that is heavier, because that is inclined, right? So gravitational force is not directly acting on that, right? So it has some component, only the component. When you take the component, so the force, the magnitude of the force is reduced, right? So that is why the 3 kilogram block is moving upwards, up along the plane, and this is moving downwards. So we get the acceleration minus 1. So we just need a magnitude of the acceleration, right? So direction doesn't matter. So if you only write the magnitude of the acceleration, so that is just 1 meter per second square. So that is the acceleration of both the blocks, right? The magnitudes of acceleration of both the blocks, that is 1 meter per second square. Okay. The force between the clamp and the pulley of mass m given in the figure is. Here we have a pulley attached to a clamp, and there is a string which is going over this pulley, and a mass is attached to the end of the string. Okay. Now we have to find the force between this pulley and this clamp. What is the nature of this force? That is the normal reaction, right? When these two objects, right, the pulley and the clamp come in contact, one exerts force on the other. So that is the normal reaction, right? That normal reaction is what we need to find. Okay, yes, let us consider this pulley. What are the forces acting on this pulley? There is a tension force due to the string, the vertical part of the string. So that exerts tension force in the downward direction. And also we have the tension force due to the horizontal part of the string in this direction, horizontal direction, and we have the gravitational force mg in the downward direction, and the normal reaction between the pulley and the clamp, right? These are the forces acting on this pulley, right? But these forces act in different directions. See, we have to take the components, right, in one particular direction, horizontal or vertical. But for a change, let us use the vector form, right? So use the vector form of all the forces, but the total force must be 0 because this pulley is in equilibrium, right? That means if you add all the vector form of the forces, right, then the total will be 0. Okay, yes, let us consider the force vectors. What are the forces acting on this pulley? Okay, so we are considering all the forces on this pulley. Now there is a gravitational force in the vertically downward direction. Okay, so that means, so you take the horizontal direction to be I cap, right? So horizontal positive direction, that is I cap, unit vector along the positive x-axis, right, horizontal direction. Similarly, the vertically upward direction is taken as j cap. That means what is the force? mg acting in the downward direction. That means that is minus mg j cap. So minus j cap is the downward direction, minus mg j cap. Similarly, the tension force is also acting in the vertically downward direction. So minus t j cap. Similarly, there is a tension force in the horizontal direction, right, the negative x direction. So negative I cap. So minus t I cap. Similarly, and there is a normal force between these two, but we don't know the direction. So what is the normal force? So that is taken as the reaction force. So you can take it as r vector for the time being, r vector, but this total must be equal to 0. Okay.
What's the direction of this reaction force?
That is what we don't know. We have to find that r vector only. So we don't know the direction. That depends on the other vectors. That's why we have simply taken it as r vector. We have not attached any direction to that, right? So we will find r vector. From that we will come to know what the direction of r is. Okay, yes. Now let us simplify that. So what is r vector? So that is, so r vector equals, so this one, so t I cap and yeah, plus mg plus t j cap. Okay, so this is r vector. Okay, yes, but what is t? So t is not known, right? So we have to find t, tension. For that we will consider that block M, right? So that block has what are the forces acting on that block? Again, gravitational force in the downward direction and also the tension force in the upward direction. So for the block M, so the gravitational force mg is acting in the downward direction minus the tension acting in the upward direction. So that must be equal to 0 because that is in equilibrium. So T is mg only. So that T can be substituted here. So this T is mg. So that T can be substituted here in this expression. So that will give you our required answer. That's all. So that means r vector equals, so this is mg I cap plus this T is mg plus mg j cap. So that is our required the reaction force or the normal force between the pulley and the clamp. Okay, so that is the answer. But if you just need the magnitude of the acceleration, we can find the magnitude of this force, right? So we can simply take the magnitude of this vector. So magnitude of this r vector, so that equals, so that is square root of, okay, so this square plus this square. Okay, so we'll get mg square plus, so square of this, so that is mg plus this mg square. Okay, so that's all. So we can take g square, right? G square is the common value, so we can take it out. So g square root of this is m square plus this will become m plus small m is, yeah, that's all. So this is the magnitude of the force between the clamp and the pulley. Okay, so that is our required answer. Okay, yes. Now this can also be done without using this vector form, right? So just for a change we did this. So usually we take the components in one particular direction, like the horizontal and vertical direction, and then the total force is 0. See, for example, see, alternatively we can do this question by this method. Okay, alternatively, see, let us take the horizontal direction. So what are the forces acting in the horizontal direction on this pulley? See, the component of R in the horizontal direction. We don't know what direction R makes with the horizontal. We assume that direction to be, say, theta, right? Theta is the angle. So R cos theta, so that is the horizontal force, and against which we have the tension force R cos theta, and tension force, they balance. So that means R cos theta equal to the tension. Okay, but the tension is same as mg. Okay, that we have already done. So tension is same as mg. Okay, so using that. Okay, yes. Now similarly we consider the vertical. So if you consider the vertical direction, so what are the forces acting in the vertical direction? So that is the gravitation force in the downward direction, and the reaction force has the vertical component R sin theta. Horizontal R cos theta, vertical R sin theta. So R sin theta is the vertically upward direction, R sin theta, and similarly vertically downward direction we have mg, right? Gravitational force mg, and also the tension in the downward direction. So that is that equals mg in the downward direction plus tension in the downward direction. Okay, so that is same as, but again we can write mg plus tension. So what is the tension here? So that is same as mg. So that's all. We have got R cos theta, R sin theta. Now to remove this theta, we don't want theta, so we want to eliminate this theta. How to eliminate this theta? You can square and add. Okay, if you square and add sin square plus cos square, that will become 1. So if you square and add, r square cos square theta, r square sin square theta, so that will give you the value r square. So that equals, so that square, so square root of, okay, same thing. So mg square, this is mg plus mg square. Okay, so that's all. So that is the same answer, right? So here, so that can also be done considering two different directions, but here we don't consider the direction separately, we consider both the horizontal and the vertical directions together. So that is what is the vector form, right? So this is one of the methods of doing it, so that can also be done. So anyway, the answer is here g square root of m square plus m plus small m square, right? So that is the answer. The acceleration of the block of mass capital M given in the figure is. Here two blocks are connected by a string, but one of the blocks is on the ground, so that is constrained to move only on the ground. So the acceleration of that block is in the horizontal direction, whereas the other block can move only in the upward or downward direction, so its acceleration is in the vertical direction. Okay, so we have done similar questions in normal reaction also, the constrained motion. So we have to find the relation between the accelerations of these two blocks. Okay, they are not equal, unlike the basic Atwood machine. Here the accelerations are related, but they are not same. So the first thing is to find the relation between these two accelerations. We have already done this type of question using two methods, right? One is using the basic algebraic method using variables, the other one is taking the component along the string. So there we found the component along the normal, right? Here we find the components of the accelerations along the string. So these are the two methods. Let us do both the methods. So here, see, what are the constant here? The length of the string is constant, right? L. So let us take the length of the string to be L, which is the constant value, and also the height of the pulley from the ground, so that is taken as h. Okay, h is the height of the pulley from the ground. Okay, now so this portion, the block of mass m, small m, so that is at a distance, say x from the ground. Okay, that is x, that is a variable, so that is what determines the velocity of that or the acceleration of that block. Okay, so that is x. That means the height, right? So the same block m is at a distance h minus x from the pulley. Okay, h minus x. That means what is this length? This part of the string, so that has length L. L is the total length of the string minus that portion h minus x. L minus of h minus x, that is this part of the string, and also this horizontal distance is taken as y. So we filled this right angle triangle. This is a right angle triangle. So there is a relation between all these values, right? So use Pythagoras theorem. So what is this height? So that is h. What is this base? So that is y. What is this hypotenuse? L minus of that h plus x. So use Pythagoras theorem to relate them. So what is the relation? So that is y square plus that height h square. So that equals L minus h plus x square. So that is Pythagoras theorem. That's all. Okay, yes. Now we have to differentiate this. So what is the derivative? So 2y dy by dx. H derivative is 0 because that is a constant. So that equals, this derivative is 2 multiplied by L minus h plus x. See, L and h are constants. Derivative of x, that is dx divided by dt. Okay, so with respect to t, right, not x time. with respect to time. So now we've got the relation. But what is dy by dt? So that is the velocity of the block of mass capital M, because as y decreases, this m moves. As this m moves in the horizontal direction, y decreases, which means the rate of change of this y, so that is in the opposite direction. The y decreases, not increases. So y decreases, the velocity increases. That means dy by dt is the negative of the velocity of the block capital M, right? Yes, that means this 2 can be cancelled. This is y multiplied by dy by dt is minus of the velocity of the block of mass capital M, right? Minus, because y decreases. The block is moving in this direction, so y decreases. So that equals, so here, so this is same, L minus h plus x multiplied by, again x also decreases. As that block of mass small m moves downwards, x decreases. That means that is the negative of the velocity of the minus of v m. Okay, so that's all. So that means the negative sign anyway is gone. So vm is equal to, so this is L minus h plus x divided by y multiplied by Vm. So this is the relation. But what is L minus h plus x divided by y? So this is the hypotenuse of the triangle, and divided by y is the base. Hypotenuse divided by base, right? That is the secant theta, right? So that means, so this is the relation, right? Secant theta Vm equal to secant theta multiplied by y. This is the relation between their velocities. Okay, yes. So now we have to differentiate to get the relation between the accelerations. Okay, now the acceleration. So when you differentiate again, we are differentiating again. So am equals, so this is secant theta multiplied by, if you differentiate Vm, that will become acceleration. Acceleration m plus, this is product rule, right? Product rule, multiplication, uv. So Vm multiplied by acceleration of this. So Vm multiplied by the acceleration of secant theta, that is secant theta tan theta. Okay, because theta is not a constant, it is a variable. Okay, this is the relation between the acceleration. But this Vm is 0 here, because this system is released from this position, which means at that position, right, at that situation, the initial velocity is 0. It is released from that position. That means initial velocity is 0. That is why this term will become 0. Okay, if this is some intermediate situation, then this may not be 0, but the system is released from this position. That means the velocity, the initial velocity is 0. So that is why this term is 0. Only this is the relation. So the acceleration of the block of mass capital M is equal to secant theta multiplied by the acceleration of this small m, right? Yes. So this is the relation between the accelerations. Okay, yes. Now we will not do all these steps, right? We will directly write. So we will use this method instead. See, mostly we use this method only. See, the accelerations of the blocks, the accelerations of the blocks along the string are same, or we can say the relative acceleration is 0, the relative acceleration of both the blocks along the string, so that is 0, or the accelerations of both these blocks along the string, which means components of the acceleration of this block and that block are not same. But if you take the components of these acceleration along the string, because the string is moving in this direction, right? So that means the acceleration along the string, whatever is the change in position in that direction of the string, that is the same change in position on the other end also, right? Because the string length is fixed. So acceleration component of this block in the direction of the string is same as the acceleration component of that block in the direction of the string. Okay, yes. You tell me, what is the acceleration component of that block of mass smaller? So what is the acceleration component? See, the acceleration is in the downward direction. That is same as the direction of the string also. The string also is in the downward direction. The acceleration is also in the downward direction, which means same acceleration. The component of acceleration is the same as the acceleration itself. That means that is the acceleration of small m. That equals the acceleration component of this block in the direction of the string, but this time this block is moving in this direction. It has acceleration in the horizontal direction, but the string is in this direction. So we have to take its component. What is the component? Theta. Theta is the angle, so cos theta, right? Acceleration in this direction multiplied by cos theta. So that's a, so cos theta multiplied by, so this is a capital M multiplied by cos theta. So that's all, that is the relation between the accelerations of these two blocks. So that's what we got here, am equal to sec theta multiplied by m, or this am equal to cos theta multiplied by a capital M. So that's what we've got here. So this relation is important, right? Mostly we use this method only. So who wants to do all these calculations? But it's better to know all these methods. We don't know when these methods are required. So this is the relation between the acceleration. That's all. Now you write the equation, you will get the answer for that block of mass small m. So what is the, yes, so what are the forces acting on the block? So that is moving in the downward direction, mg in the downward direction. So mg minus tension in the upward direction, that equals mass times the acceleration of the block. So that acceleration is a, okay, a small m. Okay, yes. Now, so similarly the other one. So other one, what are the forces acting on the block? So that is the tension force in this direction, but we have to take its component because the object is moving in the horizontal direction. Take the component of tension, T cos theta, T cos theta. Okay, so that is for this mass, T cos theta, and that is the only force, right? No other force, right? Because the gravitational force in the downward direction, but the object is moving in the perpendicular direction. So T cos theta is the only force in the horizontal direction. So that must be equal to mass times the acceleration. The acceleration is this one. So that's all. So now what do we want? So we don't want the tension here. So we eliminate this tension, you will get our required answer. Okay, yes. Now what do we do? So this implies, yeah, so mg t, that t can be substituted here. Okay, so substitute, or this value of t can be substituted here. So this becomes mg minus tension T. So T equal to m am divided by cos theta. Okay, m am divided by cos theta, that equals m multiplied by this acceleration of m, right? That is same as the acceleration capital M multiplied by cos theta. That can also be substituted, m cos theta. Okay, so that's also simplified to get this am. Okay, so what we want is this am. So that will become, so mg equals, so you take it to the other side. So if you take am common, so that will become, so small m cos theta plus capital M 1 divided by cos theta. That can be written as secant theta. So that's all. So this will give you our required acceleration, a capital M. So that equals mg divided by this value, right? M cos theta plus this capital M secant theta. Okay, so that's all. So this is the acceleration of the block of mass capital M. So that is the required answer. Okay. If alpha is the value of the angle theta for which the system is in equilibrium, find the value of alpha. If the system is released when the angle is alpha by 2, find the acceleration of the block on the right. There are two questions here. So first of all, we need to find the angle theta for which this system is in equilibrium. Now the blocks at the two ends, they move with acceleration, say a, same acceleration. Both the blocks by symmetry, they move with the same acceleration, say a, in the downward direction. But this block is moving in the upward direction, but not along the string. So their accelerations are not same. The middle one has different acceleration. So we have to find the relation between these accelerations. Okay, so like we did earlier, what do you do? This object is moving in the upward direction. Okay, but first of all, the system is in equilibrium. First of all, let's find the angle theta for which the system is in equilibrium. Later on, we can find the acceleration. Yes, now what are the forces acting on the middle block? So that is gravitation force in the downward direction, and also the components of the tensions, both the sides, in the vertically upward direction, because the object is moving in the upward direction, but the tension is acting in different direction. We have to take the components of the tension. Okay, so the block in the middle. Okay, so this middle block, what are the forces? The 2t, right? T cos theta. T cos theta is the component of the tension in the direction of its motion, T cos theta. But this side also we have a tension, T cos theta. So 2t cos theta. 2t cos theta is the force acting in the vertically upward direction. Downward we have a gravitational force, so that is minus mg. So that is the total force acting on the middle block. So that equals 0. Okay, so this is the middle block. Okay, so we call it okay, middle block. Okay, so middle block. Okay, So the block at the right end, the block at the right, okay, right block, okay, the block at the right end or left end, any one block, this or that, okay. So because both have the same acceleration, now what are the forces acting on the block? So that is suppose moving in the downward direction, so mg in the downward direction, so mg minus the tension is acting in the upward direction, so minus T, so that equals 0, because again they are in equilibrium, so that's all. So now we don't want the tension, right? So we want the theta value, so you just have to substitute this tension here. So this gives, so we can substitute this here, this value of T can be substituted here, you get 2T, but T is mg, 2 mg cos theta equals mg. So cos theta equals mg, sorry, cos theta equals mg gets cancelled, so 1 by 2. So that gives you the value of theta. So that is, okay, so theta is 60 degrees. So that is the answer to the first question. If the angle theta is 60 degrees, all the blocks will be in equilibrium. So that is the answer to the first question. Okay, done. Now, if that is the value of alpha, right, because the angle for which the system is in equilibrium, so that is given to be alpha. So alpha is 60 degree. Okay, done. Now the next question, if the angle is 30 degree, half of this angle, right, you make the angle 30 degree, the system is released from that position, okay, then you have to find the acceleration of the blocks. Okay, so how will you find it? Say now when theta equal to half of this angle, which is 30 degree, when theta equal to 30 degree, now we will find the acceleration. First of all, like we did earlier, we have to find the relation between the acceleration. Suppose the acceleration of these two blocks, so that is A, and the acceleration of the middle block is A1 in the opposite direction. Okay, what do we have to do? Find the relation using the components of these accelerations in the direction of the string. Okay, along the string you find the components and they are equal. What is the component of the acceleration in the upward direction along the string? So that is A1 cos theta, A1 component, A1 cos theta. So that is A1 cos theta. So let me write here. So A1 cos theta is the acceleration component of the middle block in along the string. What is the acceleration component of the other two blocks along the string? That is A only, right? Because they are already moving along the string only. So that means A. So that's all. This is the relation. Okay, A1 cos theta equal to A. So that can be used in the equation. Yes. Now let us write all the forces acting on this block, middle block. What are the forces acting on the middle block? So that is same thing, 2t cos, but this time theta is known. Okay. So the forces acting on the block are this one, 2t cos, the angle theta is 30 degree. Okay, minus mg, that equals mass times the acceleration of the middle block. So that is taken as A1, but what is A1? What is A1? From this we can write the value of A1. So A1 equals m A secant theta, because A1 equal to A divided by cos theta, so A secant theta. Okay, done. Now similarly, for this is for the middle block. Okay, now the other two blocks, any one of the blocks you take. What is the acceleration? So A in the downward direction, so mg downward direction minus tension in the upward direction. So that equals the mass times the acceleration, that is A. Okay, so that's all. So if you solve these two equations, you should be able to get the answer. Okay, yes. Now what can be done? So cos 30, that is root 3 by 2. So this tension can be substituted here in this equation. So if you solve these two equations, so this T can be substituted here. So if you substitute this value here, so we'll get 2T. So 2 multiplied by T. T is what? mg minus ma. Multiplied by cos 30, which is root 3 divided by 2 minus mg. So that equals, so ma secant theta, ma secant theta. Okay, so what we need is the value of A, right? So what we do, so let's simplify this, take all these terms to the other side. So we'll get our required answer 2 mg, okay, root 3 by 2. So that if you multiply 2 mg, the 2 gets cancelled, root 3 mg. So this is root 3 mg minus mg. So we can write root 3 minus 1 multiplied by mg. So now this term can be taken to the other side. This is root 3 ma, because 2 gets cancelled, root 3 ma. So here we have, okay, so let us simplify this. Yeah, so that equals root 3 ma plus this is ma. Now secant theta, but theta is known, right? So I am not substituted there. So theta is 30 degree. So substitute 30 degree there. So that is secant 30 degree, right? So root 3 by 2, reciprocal of that, 2 by root 3. So that's all. So this will give you our required acceleration. This m gets cancelled. So it is root 3 plus 2 by root 3. So let me write this here. Root 3, okay. Yeah, root 3 plus 2 by root 3 multiplied by a. 2 by root 3 multiplied by a. Okay, so that equals root 3 minus 1 times g. Root 3 minus 1 multiplied by g. So what do you get this value? So this is 3 plus 2, 5. 5a divided by root 3. So 5a is equal to, 5a equal to root 3 minus 1 multiplied by root 3 multiplied by g. So that's all. So that will give you required acceleration, a equal to root 3 multiplied by root 3 minus 1 divided by 5 multiplied by g. So that is the required acceleration of these two blocks, right? So at the right hand and the left hand, these two blocks have the same acceleration, a, root 3 multiplied by root 3 minus 1 divided by 5g. So that is the answer, okay? A ring of mass m which can slide along the smooth horizontal rod is attached with a block of mass capital M by a string as given in the figure. The acceleration of the ring is. Here a ring is attached to a string. The ring can move in the horizontal direction only along this rod, and the other end of the string is attached to a block of mass m. This block can move in the vertical direction only. Now just like the other questions, this is also a question of constrained motion. So we have to find the relation between the accelerations of these two objects, right? The block and the ring. Now we will do by both the methods, though the second method is easier, finding the components of these two accelerations along this string, right? So they are equal. Now we will do by both the methods for this question. See, now let us take the distances, right? So first distance. So the pulley, right, is at a distance c from the horizontal rod, okay? That distance is c, and also the block, which is a constant, the c is constant, right? That distance is fixed. Now let us take the distance from the pulley to this block, that is taken as y, but that is a variable, right? Because as the pulley moves down, so y increases. So y is a variable. Now we also take the horizontal distance of that ring, so that distance is taken as x. Now the length of the string is a constant, okay? That is L. L is the length of the string. Now, so that means this portion of the string, so that is L minus y, okay? Total length is L minus y. So we have a right angle triangle, we can use Pythagoras theorem. So similar to the other question, right? So what is that Pythagoras theorem here? So that is L minus y, that is hypotenuse square. So that equals, so that distance c square plus x square. So that's it. Now we just differentiate it to get the relation. So just differentiate it. This is 2 times L minus y multiplied by the derivative of this is minus dy by dt. So that equals, derivative of c is constant, so 2x dx by dt. Okay, but what is this dy by dt? So dy by dt is the negative of the velocity, sorry, not negative, it is the velocity of the block m, because as y increases, the block is moving downwards, right? As y increases, the velocity, right, the object changes position. So that means the velocity of y, velocity of the block m is the rate of change of y. So dy by dt is the velocity of the block m. So that is 2 can be cancelled. So that is L minus y. This is minus of v, the velocity of the mass m. Okay, that equals x multiplied by, what is dx by dt? So that is the velocity of the ring, right? But that is negative of that because x decreases. As the velocity increases, x decreases. So x decreases, that means this is minus of the velocity of the ring of mass small m. Right? That is a relation. Okay, yes. Now what is the relation? Yes. So Vm equal to, so this is x divided by L minus y multiplied by V small m. Okay, but what is x divided by L minus y? That is for the triangle adjacent side. Okay, adjacent side divided by the hypotenuse, adjacent side by hypotenuse. So that is cos, right? Cos theta. If that angle made by that string with the horizontal is taken as theta, so this is cos theta. So the velocity of the m, right, that is the block. So that equals cos theta multiplied by the velocity of the ring. Okay, so that is done. That is the relation. But the same relation for acceleration also, because so this system is released from that position. So that means at that point the velocity is taken to be, initial velocity is taken to be 0. So the acceleration of m equals so cos theta multiplied by the velocity of this thing, that if you differentiate we get the acceleration of m plus 0, the other value is 0 because this multiplied by derivative of this is this one. Now Vm multiplied by derivative of cos theta, but Vm initial position, right, it is released from that position, so initial velocity is taken to be 0. That means this is the relation, but this relation can be found using the other method also, right, the acceleration components. So the acceleration components of both these objects along the string. What are the acceleration components of the, see, acceleration component of the ring along the string? What is that? The angle is theta. So acceleration in this direction, take its component along the string. So that is am cos theta, right? So am cos theta. That must be equal to the acceleration component of the other object, that is the block, but that is along the string only, so that has the same direction as the string only, so that means that is am itself. Okay, so that's also, that is the relation am equal to cos theta multiplied by, so this is the relation between the accelerations. Okay, now let us use our basic equations, right, for the block m. So what is the downward force? So that is mg minus the upward tension force, so that is T. So that equals the mass times the acceleration. Mass times the acceleration of that block, so that is taken as capital M. Okay, now similarly we can write the equation for the other ring also. So ring is moving in this direction, okay, moving in this direction, but the tension is acting in this direction. So take the tension component in the direction of motion. So that is T cos theta, right? T cos theta is only force in the horizontal direction. So T cos theta. So that equals mass times the acceleration. So mass times the acceleration of that ring, so that is am. But these two are related, okay, am, these two are related, so we can use that relation also here. Okay, now let us simplify this. Let us substitute this value of T here in this equation, okay, like we did earlier, same calculations here. So mg minus T. What is this T? So from this, so am this T, right, divided by cos theta, so that equals m multiplied by this am. So what is am? The acceleration of the block, so that is written as, so here am equal to small am cos theta, okay, so am cos theta. Okay, so that will simplify this, you get required acceleration am, right? So this gives you the value of am, that equals mg, this mg divided by, so it taken to the other side, it is m, capital M cos theta plus small m 1 by cos theta, that is secant theta, so that is m cos theta plus the small m 1 by cos theta, that is secant theta. So that's all. So this is the acceleration of small m, that means the acceleration of the ring, right? So that is the answer, mg divided by m cos theta plus small m secant theta. So that's it. If the man and the monkey given in the figure hold on to the rope, their acceleration is 2 meters per second square. Find the acceleration with which the monkey has to climb up the rope to keep the man in equilibrium. If the monkey climbs up with the acceleration twice that of the man, find the acceleration of the monkey. There are three situations given here and two questions are asked. In the first case, the man and monkey are moving with some acceleration 2 meters per second square. That means they are not trying to do anything. So just because of their own weight and tension, they are moving up or down with the acceleration. So one of them must be moving upwards, the other one is moving downwards. Suppose the man is moving downwards. So whichever is heavier, that will move downwards, right? So the man is moving downwards and the monkey is moving upwards with the same acceleration 2 meters per second square, right? So that is the first situation. Okay, so in that case, see what is the man, okay? For the man, what are the forces acting on the man? So the gravitation force in the downward direction, so that is mg. The tension is acting in the upward direction, so mg minus t, so that must be equal to the mass times the acceleration. So the acceleration is given, so that is 2. Okay, so this is for the man. Similarly for the monkey, see for the monkey, so the tension force is acting in the upward direction, the monkey is moving in the upward direction, so the tension first, so T minus the gravitation force downward direction, that must be equal to the mass of the monkey multiplied by 2, right? Same acceleration 2. Okay, yes. Now we don't need the tension, we just need the relation between these two masses, right? So we just have to add these two equations. So what do you get? M minus m multiplied by g equals 2 multiplied by m plus m. Okay, yes. Now this gives you some relation between the masses of these two objects, right? Yes. Now what do you get? So this is 10. So this is 5m minus, so 5 capital M minus 5m. So that equals, this is m plus m, right? So taking the value of g to be 10. So what is the relation? So this is 4m equal to 6m, right? So that means, so m divided by m. So this ratio is equal to, right, so this is 6 by 4 or 3 by 2. So there is some relation between the mass of these two people, right? So one is a man, the other one is a monkey. So this relation is there, which we can use later on if required. Okay, so that is the first situation. Okay, in the second case, so that means the first question, now we have to keep the man in equilibrium. In this case, what happens? The man is moving down with some acceleration, but now we have to keep the man in equilibrium, so he has to stay in the same position. For that, the monkey has to climb up with some acceleration. With what acceleration should it climb up so that the man is in equilibrium? Okay, so the man is in equilibrium, so that means, so again for the man is in equilibrium, so that means the tension, so the tension in the rope, so tension must balance the gravitational force, so T minus mg, so that must be equal to 0. Okay, so let me take T1, right, just to avoid confusion. The first case the tension is T, the second case we have different tension, right? So T1 you take, so that means T1 equals mg. Okay, that is one relation. Now similarly for the monkey, so monkey is moving up with acceleration. See, upward force, that is the tension force, so same tension T1, and a downward gravitation force mg. So that must be equal to the mass times the acceleration. So that is what we need to find. This acceleration is what we need to find. Okay, let us find this acceleration. Now we just subtract it. Okay, if you subtract it, so what will you get? Will you get the value of a? So let us simplify this. So if you do that, so we will get from this to this. So we get m minus m times g equals mass times the acceleration. So that's it. I think this should give you the value of acceleration, because we know that, so this relation is known, m is to m, that ratio is known, which is 3 is to 2. So we can use that, or we can divide by this m. So if you divide by this m, so m divided by m minus 1 multiplied by g is 10, so that equals the acceleration. So that gives you our required acceleration, a equal to, so m by m is what, 3 by 2, so 3 by 2 minus 1 by 2 multiplied by 10, so that is 5. So this is the required answer, right? So that is the acceleration with which the monkey has to climb so that the man is kept in equilibrium, right? So that is the answer to the first question. Now similarly, so the next one, so both of them are moving up with some acceleration, but these accelerations are related. The monkey is moving up with acceleration twice that of man. So again we'll write the equation, say for man, so the tension, the upward direction, so T2 minus the gravitational force in the downward direction, that must be equal to the mass times the acceleration. So we'll take the acceleration to be, okay, so a only, so a is the acceleration of the man, so not to be confused with this a, so or we can use a different letter. So this is for the man. Again for the monkey, so again tension minus mg in the downward direction equals mass times the acceleration of the monkey is twice that of man, which means here it is a, so that means 2a here. So now we have to eliminate this T2, right? Tension is not required, so we can simply again add or subtract these two equations, this minus this, so that will give you m minus m times g equals, so this is a, if you take out, so you will get 2m minus m. Okay, that's all, that is the relation. But we already got the relation between m and m. So m by m is 3 by 2. What do? You divide both the sides by small m, right? If you divide by small m divided by m, so that is 3 by 2, and this m by m, that is 1. So like that, right? We can simply divide both the sides by small m. So that will give you, so this m divided by m, so that is 3 by 2 minus this m by small m, that is 1, multiplied by the g value is taken as 10, the acceleration multiplied by, this is 2 minus 3 by 2 again. Okay, see, we are dividing by small m, both the sides, that's all. So that will give you this relation. That will give you our required acceleration. This is 1 by 2, so the acceleration is 10. Okay, yes, but that is the acceleration of the man, right? But we want the acceleration of the monkey, right? That is 2 times a, so 2 times 10, so 2a is what we need, so 2a equals 20. So that's also, that is the answer, the acceleration of the monkey. So that the man and monkey move up with some acceleration which are related, right? One is twice the other, so 20 is the answer to the second question, and also 5. So that is the answer to the first question. Okay. A block of mass 80 kg and a ladder of mass 30 kg are attached to the two ends of a string. A man of mass 50 kg climbs up the ladder with acceleration 2 meter per second square relative to the ladder. The acceleration of the block is. Here we have a string over a pulley, one end of which is attached to a block of mass 80 kg. The other end is attached to a ladder. This man is standing on the ladder, right? Now the combined mass of the man and the ladder, that is also 80 kg. So both the sides we have the mass 80 kg. That means the system as such is in equilibrium. But the man starts climbing now, right? The man starts climbing on the ladder. So how will he climb? He applies a force on the ladder in the downward direction. That is the normal reaction between him and the ladder. He applies force in the downward direction, so he moves upwards, so the ladder moves downwards, right? Now the ladder is directly attached to the block with the string. That means the acceleration of the ladder is same as the acceleration of the block, but in the opposite direction. So acceleration of the ladder and the block are same, but the man has different acceleration. He is moving with acceleration 2 meter per second square, but that 2 meter per second square is only the relative acceleration with respect to the ladder. His actual acceleration may be different, so we have to subtract. The ladder is moving in the opposite direction, so his actual acceleration is 2 minus the acceleration of the ladder, right? 2 minus a. 2 minus a is the acceleration of the actual acceleration of the man. The ladder has downward acceleration a, the block has upward acceleration a, right? That's all. Now let us write the equation for all the three objects, right? The ladder, block and the man. Okay, yes. Now for the block, what are the forces acting on the block? So we have the gravitation force. The block is moving in the upward direction, so we take the upward force, that is the tension force, right? Tension minus the gravitational force in the downward direction, so that is 80 kg mass, so 80 g. So that equals, mass is 80 multiplied by the acceleration is taken as a only. Okay, a is the acceleration of the block. Now for that ladder, so what are the forces acting on the ladder? The ladder is moving downwards, right? So then the gravitational force, so 30 g, and then the person is applying a force, normal force in the downward direction. The normal force applied by the person is also in the downward direction, right? He is moving upwards, which means he is applying a force in the downward direction. So that is same as n, so that is in the downward direction, so n. Now the tension is acting in the upward direction, right? Yes. Now minus t, so that equals mass, that is 30 multiplied by same a. So the acceleration of the block and the ladder both are same, right? So that is for the ladder. Now for the man, what are the forces acting on the man? So he is moving upwards, which means, so the only due to the normal force, right? He is not directly attached to the string, no tension. So he is moving upward because of the normal force. He is applying a force on the ladder, so ladder applies a force on him in the upward direction. So normal force is what makes him move in the upward direction, normal force in the upward direction, and the weight of that person, so that is minus 50 g. So that equals mass of the man, which is 50 again, multiplied by the acceleration of the man. See, 2 meter per second square, that is the relative acceleration with respect to the ladder, but the ladder is moving down with acceleration a, so that means the actual acceleration of the man is 2 minus a. You understand? Because they are in the opposite direction. The actual acceleration is 2 minus the acceleration of that ladder, so 2 minus a. So that's all. These are the three equations which we need to solve to get the value of a. I think a is what we need to find, the acceleration of the block, that is a. So a we have to find by solving this equation. So how will you solve? So we don't want the tension and the normal force. So if you add these two, the tension will get cancelled, okay, and then if you subtract, we get the normal will also be eliminated. So first we add these two equations. Okay, so if you add the first two equations, first equation and second equation, if you add up, the tension will get cancelled. So 30 g minus 80 g, so that equals minus 50 g plus n, that equals 80 plus 30, so 110 a. Okay, so that's all. Now you add this thing. So with this we add the third equation. Okay, so this is the third equation, we just add this. So not add, right? We subtract. Okay, so you subtract this equation. So we subtracted minus. So we get So this minus this, so this minus 50g, this also minus 50g, n plus n, so that means if you subtract you get 0. So 0 is equal to, so if you add this we'll get 50 times 2, so 100 minus 50a, and then if you subtract minus 110a, so that gives you our required acceleration. So that equal to 100 divided by 50 plus 110, so 160. So that gives you the answer. 10 divided by 16 or 5 by 8. So that's also, that is the acceleration of the block or the ladder, right? Both are same. So that is the answer. The force applied by the man given in the figure to keep the system in equilibrium is. Here a man is standing on a block or a plank which is attached to a string held by that person. Now he is applying a force on the string in the downward direction. So this force is what creates a tension in the string. So it is because of this tension that this plank is staying in that position. Otherwise it will fall down, right? So this system is in equilibrium. Now we have to find the amount of force applied by this person on this string. So that is same as the tension force, right? The force applied by this person is same as the tension force because the tension is created by the force applied by the person. So what we need to find essentially is the tension on the string. Okay,
The physics doesn't seem to be right here.
yes, this plank seems to be staying horizontal without any support. Maybe the actual situation is something like this. Just for convenience we draw like that, but the situations are same, right? So we can consider this situation, but for convenience, for our calculation, we'll use that diagram. Okay, yes, now this plank is there. Now the total force acting on this object is 0 because this is in equilibrium. What are the forces acting on this block? Okay, yes, so this block or this plank, whatever, so block, what are the forces acting on this block? Now the gravitational force is acting in the downward direction, so that is mg. And then this tension force is acting in the upward direction, right? So upward direction. And also this man is standing on this plank, which means he is applying a force in the downward direction, right? Normal force due to this person on that plank. So that is in the downward direction, so plus m. So this is the total force acting on that block, so that is 0. Okay, so this is on the block. Okay, now the man. What are the forces acting on this man? Now the tension force, right? Tension force is what is lifting him, right? Tension force in the upward direction, and also the gravitational force due to that person in the downward direction, and also normal force due to the plank. So these are the forces acting on the person. Now, so there is a tension force in the upward direction, T, and also gravitational force in the downward direction, so minus mg, and also the normal force due to that plank, so that is in the upward direction, so plus n, that must be equal to 0. Okay, so that's all. Now we solve these two equations to get our required tension. Okay, yes, what we need is the tension force or the force exerted by that man. Both are same here. Now so we can simply subtract it. We don't want the normal reaction, so we can subtract it. So we get mg minus 2t plus mg equals 0. So this gives you our required tension equals m plus m multiplied by g divided by 2. So that is the tension, but the tension is same as the force only, right? Because the tension is created on the string because of the force applied by the person only, so same. So T or F, so both are equal to this one, m plus m times g divided by 2. So that is the answer. The blocks given in the figure are released when they are at the same horizontal level. The maximum height from the ground reached by the block of mass m is. Here two blocks are given which are connected by a string. Initially these two blocks are at the same horizontal level, right? That is 20 centimeter above the ground. Now if this system is let go, what will happen? The heavier mass, that is the block with mass 3m kilogram, that will move in the downward direction. The other block will move in the upward direction. Now we have to find the maximum height reached by this mass, right? So the block with the mass m kilogram. So what is the maximum height reached by this object? So what is the maximum height?
20 plus 20, 40 centimeter.
See, when that block reaches ground, it is covered a distance of 20 centimeter. So this block will also move up by a distance of 20 centimeter. Already it is at a distance of 20 centimeter from the ground. So 20 plus 20, so 40 centimeter. So that is the answer. No, see, when that block hits the ground, it hits the ground with certain velocity, right? So now this block will also move up with certain velocity until that block hits the ground. So the string is taut. That means there will be a tension force in the upward direction. Now once it reaches the height of 20 centimeter above that level, then the string becomes slack, but the block will have certain velocity at that point, right? So it will continue moving under only gravity. The gravitational force is the only force acting on the object. So when it reaches the height of 40 centimeter from the ground, it will not stop at that point because it has certain velocity. It will continue moving from that point onwards. But from that point onwards, not the tension force, only the gravitational force is acting on the object, right? So until that moment, so the acceleration is due to the gravitational force and the tension force. But it reaches the maximum height of 40 centimeter, it will move up with acceleration only due to the gravitational force. You understand? So it will move above that 40 centimeter level. So that we have to find, right? So first of all, we have to find the velocity or the speed of this block when it reaches the height 40 centimeter, and from there, so we have to find the maximum height where the acceleration is only due to the gravitational force. Okay, yes. Now see, what is the velocity? Let us find the velocity. First of all, let us find the acceleration of the blocks, right? Yes. Now for the 3M block, right? So what are the forces acting on the block? So for the 3M block, the forces, so it is moving downwards, so that means the gravitational force. So 3mg in the downward direction minus the tension is acting in the upward direction, so minus tension equal to mass times the acceleration, 3m multiplied by the acceleration. Okay, similarly the block of mass m, so that is moving upwards, right? So the tension force in the upward direction minus the downward gravitation force mg, so that equals mass times the same acceleration. Both of them move with the same acceleration. So that moves downwards, this move upward, right? Yes. Now if you add these two, because we don't want the tension, so we can add these two, so it will become 2mg equals, so 4ma. So that gives you a required acceleration, that equals, so yeah, so this is m gets cancelled, this is g by 2, or we can say 5. Okay, 5 meter per second square. Okay, so this is the acceleration. Okay, so we found the acceleration. Now we have to find, so when it has covered a distance of 20 plus 20, right? So 40 centimeter above the ground level. Now what is the speed at that point? Which means that block, the block of mass m, covered a distance of 20 centimeter, which means 0.2 meter, right? 0.2 meter is the distance covered. When distance is known, we can find the final velocity at that point. So using this formula, we know that v square equals u square plus 2as. Okay, so that is the initially the speed is 0, right? It starts from that point. So let us find v. So v square equals 0 plus 2. The acceleration is known 5. The distance covered is 20 centimeter, that means 0.2. So that will give you our required value of v. So that equals, so 10 multiplied by 2, so root 2. So root 2 is the speed when it reaches distance, which reaches a height of 40 centimeter from the ground level. Okay, now it moves further, right? What is the distance covered, right? Let us find that distance when it reaches the maximum height. When it reaches the maximum height, at that point the speed is 0, right? Velocity becomes 0 at the maximum height, because at that point it will start to return, right? Change its direction. So that means the maximum height. So when it reaches maximum height, so the velocity, so that becomes 0. So use the same formula. So v square equal to the initial speed at that point is 0, root 2. So 0 square equals root 2 square plus 2as. So we are using the same formula here. So we are using the same for v square equals u square plus 2as. So plus 2 acceleration. What is the acceleration this time? Okay, the acceleration is only due to the gravitational force. So the acceleration is simply minus g in the opposite direction. The object is moving in the upward direction. Gravitational force in the downward direction, minus 2g. Yes, the distance. So that distance is what we need to find. So let us find that distance. So this will become, so root 2 square. So that is 2. So 2 is equal to 2 times g. So that you can say 20s. So s equals 0.1 meter. So that is the distance covered by this block above that 40 centimeter level. Over that 40 centimeter level, it has covered the distance of 0.1 meter. So what is the total distance covered by the total height? So total height equals, see, initially the object is already at a distance of 20 centimeter from the ground. Okay, yes, which means 0.2 meter. Now, when that block reaches ground, it has moved up by the same distance of 20 centimeter. So that means again 0.2. And again, over this level, right, so it has reached a distance of 0.1 meter. It covers a further distance of 0.1 meter. So that should also be added. Okay, so that's all. So this is the answer. So that equals 0.5 meter. Okay, so that's all. So that is the answer. Or we can say 50 centimeter is the maximum height reached by that object. You understand? So first of all, we need acceleration. See, when the string is taut, that means the acceleration is due to the tension and also the gravitational force. Now when it reaches the maximum height, the only acceleration is due to the gravitational force. So it still moves further, because when it reaches the height of 40 centimeter, so the velocity is not zero. The velocity is there, velocity is non-zero, which means it will continue moving. So it reaches a further distance of 0.1 meter. Okay, so the total distance from the ground level is 0.2 plus 0.2 again plus 0.1. So that is the value 50 centimeters. So that is the answer. Okay. We have done some questions on pulley block system, but only pulleys at rest. Moving pulleys we are going to talk about in the next class only. Okay.